Thank you for joining us. It's sort of in first workshop, so just doing structural solution and refinement. So what are we doing? So the overall aims of this workshop. So first of all, our primary audience is actually UK undergraduate students. So we're here to support, enhance, hopefully research projects that have happened while under sort of COVID restrictions and so on. So that's the reason we're doing it, and hopefully, so some of these things might be sort of are UK based and things, but hopefully everything else will be self-sufficient and understanding. So what do we want to try and do? So hopefully, sort of the idea of this is to get diffraction data if you have it, and how to actually solve data, and then when you have the data, what actually you can do with it, extra information that can all be done from home without any extra without needing to come into a lab or so on, as long as you've got a computer and the internet. And hopefully it'll give you some way of hopefully gaining extra information from your results to give better context and get you better results. Yeah. Okay, so as Rob has already mentioned, so basically we have session format's going to be similar each time. So a few minutes of introduction, the bulk of the time will be a demo, and hopefully the idea is that you can follow along and actually complete it at the same time if you've got an extra screen, or if needed, just watch it and then watch the video back at the end and can go through. But hopefully the pace will be at saying that you can actually follow along. There is a Q&A, and we'll also at the end give you some extra pointers to further information. So if you think you actually need to do a lot more in this area, we can point you to where you can find this information and get a sort of lot more attempts, because the one thing with crystallography is the more you attempt it, the better you get, and it takes time. So the first bit, getting it all done, is great, you can get something quite quickly, but it does take time to get stuff. And something else, if you do get stuck on following the demo, just watch it. As I say, there is a recording, it is recording at the moment, so we will give this recording as well, so you can watch it back and hopefully find what you need. So we've got 3 sessions in this thing, and today's the first one, which is how to use Olex2 to solve and refine structures. Olex2 is a freely downloadable sort of software suite of crystallographic programs, and it is great, and sort of it's meant to be so you can use it without ever typing or do minimal typing, so it can all be done using a mouse. Next week, the predominant thing will be how to use Mercury to visualize and analyze results, and then we'll do a conquest to how to do sort of searching online and looking at databases to actually look for things. So for this one, learning outcomes, hopefully we'll give you the basics tools in Olex2, so you'll be able to actually take a simple crystal structure, solve and refine it. That's the idea. And then from that data, you'll be able to say, get a good reliable result, and we'll give it in a presentable format, so you can give it report ready, so you can just sort of once you've finished, you have a picture and also all the information, you can put it together. And hopefully you'll also, while we're going along, understand how you can determine whether your structure is good or bad, although we'll do a few bits more of that next week as well. Don't have to worry too much about this slide, but basically this is a process we actually go through. So we are at the stage of data has been collected on a diffractometer, has been processed there, and so this is in a sense the final stage where you've got the integrated data and you're going to solve and refine and get a structure which you can then work with. And it is an iterative process. Sometimes you can go through this whole process sort of straight through, one step each and done. Other times you'll have to go through some of these steps sort of 10, 15, maybe even 100 times just to get the result you want. So as I say, it is an iterative process, and you can often go backwards and forwards and so on, but in the process, so hopefully we'll show you how that works. Now, what we should think is the data we're going to sort of, the demo data set we're going to go through is glycine. And we should have sent you 3 files, which is a .res file, a .hkl file, and a .cifod. The HKL file is the actual data, and that should never change. So once you've got it from the diffractometer, it's been integrated. In effect, that's the data we're comparing against, and just getting a model each time, compare against that data, see what happens. The cifod is a metadata file. it basically contains information about diffractometer use and possibly about the experiment. So generally, it will have information about sort of crystal size, color, possible things like that. And yeah, temperature data was collected at. The third file is, as I say, is a working file, and this is continuously changed. So every time you do a modification, as I say, this is an iterative process. That file will get changed, processed, you'll check again, and we'll go through the process again. So that's it. Now, this is for one instrument manufacturer. Other manufacturers might have slightly different files, but basically they all have the same sort of setup. You have a file somewhere which has the actual data, and then you have some other files which will have metadata and things that can be modified. Sometimes that all might be rolled into one, other times it's like 3 different files, but that's basically what you're going to have. If you want to follow on with the demo, as I say, it should be put into a working folder. So we sent you a zip. If you try and run with the zip, it won't work. So they have actually got to be loaded up in a working folder. And at the very top right, there's an image of glycine. If you didn't know what it is, it's possibly the most studied crystal structure out there, and so on. It's very simple and hopefully well known. So that's the introduction. Now on to the demo. Hopefully you can now see. So this is the start of Olex2. So I've opened up Olex2, just opened up the window, and now I actually need to find my data. So multiple ways. The easiest thing is file open, and I've got the thing called a sample data W, and it tells me I can see an HKL and a res. And if I actually looked at the folder, I know the CIFOD will be in there. And I can select either the HKL or the res, make sure it's in, and click open. At the moment, there's absolutely nothing on the screen, sort of on the left-hand side. So Olex is a visual sort of program, and everything you work with will be on the left-hand side. And on the right-hand side, you'll have a whole load of information. Currently, all it's telling me is it's got the sample name, title, sample data 1, and it's giving me some basic crystallographic information. So it's telling me the unit cell, it's giving me Z, their prime volume, and it's giving me some statistics about the actual integrated data. So it's telling me how far I collected the data out to, an I over sigma, an R int value, and how much data, sort of the percentage of data. Olex works on a traffic light system, so when you're looking at the values over here, you want to be seeing dark greens, but they can be red, can be sort of amber, can be light green. At the moment, the bottom set, it's all got NA, not applicable, simply because we haven't actually started the refinement. So these values there will soon be values put in there once we actually start the solving and refining. So we've got the thing on here. There's a whole load of tabs, and basically for the bulk of the program, we are going to be in the work tab. So click on it, left click, and it comes up with a whole load of new tabs. So we have solve, refine, draw, and report, and we actually go through in that order. There's a whole load of other things down the bottom, but for the moment, the first thing we actually want to do is solve the structure. So we want to be in the solve menu. So we press the arrow, just make sure everything's correct, and click. Then actually click, left click on the solve button. And the program goes away, starts solving, and on the screen you get a whole load of brown spheres. Now, if I hold the left mouse button down, and sort of somewhere in space, I can rotate of the structure, or in this case, the spheres. If I hold the right mouse button down, I can zoom in and out. And if I hold both down at the same time, I can move the structure around on itself, so without rotation. Now, you probably don't see that does look like absolutely nothing like the structure of glycine, and I would agree with you, but what are we actually seeing there? So each of these brown spheres represents an area of high electron density. If I hover over a sphere, you will hopefully get, it's not showing up on the screen, but you'd get a little window telling me what it is. If I click on one of the spheres, it changes to green, which means it's selected, and I can find out which one. What I want to know is the easiest way to do it is find out what the numbers are. I'm going to actually click on this labels on off, and now I can see that there's Q1, Q2, Q3, Q4, Q5, Q6. Now, each of these is an area of highest electron density, and as I say, at the moment, doesn't look anything like glycine. Now, the one thing is with a crystal structure is we only solve for the asymmetric unit, which is sort of in a crystal structure, you have the unit cell, which is a imaginary block that is repeating sort of translations to generate the crystal. Inside the unit cell, even smaller fragment is the asymmetric unit, and that is, if you do symmetry operations, will sort of have your molecules to actually grow the unit cell, which you can then just by translations make the crystal you want. The program doesn't actually understand sort of what you want for an asymmetric unit. It just goes to the smallest bit, but we as humans like things to be close together. So one of the best buttons on the program is this one up in the top right, where there is a circle with 4 arrows to it, and generally click on it and we get some sort of, hopefully things move close together. In this case, they're not that bad. Now, the other thing is that we're expecting, if I look at the formula, C2H5NO2, when we look for diffraction patterns, the first thing is we ignore, until right at the end, we ignore hydrogens. Absolutely don't worry about hydrogens at all. So therefore, ignoring the hydrogens, we've only got 5 other atoms we're expecting. So we've got Q1, Q6, so one of the things is possibly Q6 doesn't actually exist. I don't know. So what you can do, if I don't like it, easiest thing to do, just select it and then press delete and it disappears. That's fine. Now what I will do, try it again. Still not great, but we're going to have a try. In fact, I'm not entirely happy with this, so I'm going to try and go and do a solve again. As I say, the one thing with the program is the data itself is always there. So if we haven't got a problem, let's try again. That's looking better. I can now see what looks like the shape of glycine. You might not believe me. So one of the things you can do at the moment, they're just spheres. If you want, we can get bonds. So if you do Control Q, you'll now get bonds together. And if we do it again, all the Q peaks, these brown spheres disappear and back to this thing. So we can see whether we want bonds or not. Sometimes people prefer bonds, sometimes people don't. So I'm quite happy with that. Now, so far we haven't actually done much. We've got to sort of actually tell the program what these atoms are. At the moment, they're just imaginary atoms. We know we've got 2 carbons, a nitrogen and an oxygen. Realistically, as a first approximation, the highest area of electron density, so your Q1, will be your heaviest element. We've got an oxygen, so we select the atom, and on this toolbox work, if it's not there, so if you click toolbox work, it will minimize it. If you click it again, we've got a whole load of the elements. So generally you have the most, sort of the ones that you've actually stated are meant to be in the structure. So we're expecting it to be an oxygen, so click on it. And it's now changed from Q1 to O1 and it's gone red to be an oxygen. My initial approximation is if we're doing it 2 oxygens, therefore Q2 will be another oxygen. Might be wrong, but then, so we've got 2 oxygens, so the next thing down, Q3, will be a nitrogen. And if we're doing it correctly, the next 2, so Q4 will be a carbon and Q5 will be a carbon. Well, that looks like the basic structure of glycine. It might be, might not. How do we know? The whole point is what we actually want to do is refine it against the data. So now we've put in a predicted model and the actual thing. So the whole thing that takes the time is refining. So we go from solve to refine, has some data up here. So things like the toolbox stays remains where it is, but we have a whole load of new things. And what's the thing? Let's just press refine and see what happens. So, okay. hopefully everyone's had some sort of refinement. So what we get, you'll have seen that the atoms have slightly changed. So we've got now they're different size spheres. We've got some new Q peaks. And we also have statistics up here. So these values are now put in. So we have a shift that's in red, a goof, so goodness of fit, which is also in red. We have a max peak, which is orange, and a minimum peak, which is possibly light green, could be yellow. And we also have a value for R1 and WR2. And the final thing is there's a battery here, and this is the data to parameter ratio. And basically we want this to, by the time we finish, still be above 10, as just means you've got a good set of data, a good amount of data. So the two important, well, most of these values have some influence, but the one that most people instantly look at is this R1, and you want to get this as low as you can. Sometimes there might be a reason, and this is basically how, as a percentage, how good this model fits to your actual data. And as a first approximation, you've done one refinement set of refinement cycles. 9% is probably not too bad. Could be better, could be worse, as I say, but it's a starting position and we can see what happens. Now, when we're doing the refinement, okay, this might be correct, might be absolutely. However, how do we know that actually I've put the oxygens in the right place, carbons in the right place, nitrogens in the right place? What happens if I actually put, say, instead of this being carbon, this C4, I actually think it should be an oxygen. So all I need to do is highlight it, click as oxygen, so it changes to red, and it says it's O4 as well. And I can run the refinement cycle again, and we'll see what happens. So we now have this oxygen has grown a lot larger, which is probably a thing, but also things like the R1 has gone up, sort of now 13%. It was 9.6, so 13%. That's the thing. Good fit. And as I say, visually, we've now got a very large sphere here compared to all the others. And generally, what you actually want to see when you've actually got a good set of data and your atoms are probably correct is they all should have roughly equal spheres of sort of radius. Now, one thing that will happen is that anything that's terminal will always have generally will have a slightly larger sphere than atoms that are bound to multiple other atoms, so held within the core of the structure. Simply, so the one thing you've got to remember about crystal structure, it is still the average of billions, trillions of molecules, and they're all still vibrating because we very rarely run this at absolute zero, so they're still vibrating. So you'll get an average of their positions, so anything that's a terminal will still always vibrate slightly more. So even though there's a counter effect that actually the heavier the element, the smaller, slightly smaller it will happen. If it's at a terminal group, it will end up being slightly larger. However, as I say, so this is definitely not right. So change it back to a carbon, click refine. Okay, and off we go, and we're back to the same position. And as you say, you saw if you have an element with too much electron density, it gets larger. What happens if we do the other thing? What happens if I thought this was a carbon? So at the moment, you see it's actually probably the largest sphere. Change it to a carbon, refine it, and you see again that actually the other spheres have got larger and this one has got much smaller. And it's a symbol that if that probably means that actually you've just got, there's more electron density there than you're expecting, and it's just shrunk it all together. And you've also got actually this Q watt. So this is saying there's a large area of electron density right next to this atom. And the reason is because we're trying to tell it to be a carbon, which only has 6 electrons, and it's actually an oxygen where you've got your 8 electrons or whatever else, and with all the core stuff. So again, your R1s, this one's even higher, 13.86. So just by changing one atom, I'll go back to oxygen and refine. We can go things. That's fine. So we've got the atoms, and that's okay. So hopefully this is the correct structure. Now, something else I should let you see. if you're unhappy with the refinement cycles, so there is a history feature. I click on it, it gives a histogram. At the moment, this is where we are, this is where we started, and I can go through and cycle through which ones I want. So if I want to see when I was actually had the carbon a bit larger, I can see it. And if I want to see when I had the car, sort of just to actually visually look at them and see how the atoms change with the structures. But generally you want to be at the end and so on. So the one bit about the history is if you end up making a huge mistake and something goes horribly wrong, so if you've got two options, there's always, if you have to, you start going with the solve. But hopefully this thing, you go back a couple of steps from where you made the mistake and where it all went wrong, and you can then try again making the thing. So there is a sort of, don't think that I made a mistake, I've destroyed the structure, I've got to go right back to start. It's normally you just have to go back to the previous step, the information is there, and then we can keep going. So, I'm happy that I've actually got all my atoms correct now, which is good. So, at the moment, we're representing them as spheres, which as a first approximation is absolutely fine, but it is a very, very basic approximation. You've got whole loads of vibrations going on, the atoms are moving around and so on, and generally things. So a better approximation is to represent each of the atoms as an ellipsoid. So almost you're going to have, instead of the one parameter of the radius of the sphere, you end up with 6 parameters of an ellipsoid. So there's 3 radii and 3 angles of where the direction is. And this is a better approximation of your setup, sort of whether you've got vibrations or whether just movement in the structure, sort of the long bonds and so on. Now, where you find that is in the toolbox work. You have something that this button here that looks like an ellipsoid, also looks like a rugby ball. And next to it, there's something that looks like a sphere. So we can, again, we will try and refine it. Let's go forward, see what happens. Okay, and you see, instead of having the atoms, you've now got sort of these ellipsoids, these rugby balls. And again, you each have sort of something that looks quite sort of, hopefully they're all still similar size and similar shape, with the effect that anything at terminal will always be slightly larger. You'll notice that what's happened is that my R1 has dropped again, so it's now 7.4, so improving. I told you it takes more parameters, so our battery here has halved, because we've now got from sort of each atom, instead of effectively having 1 parameter for the size and then 3 for position space, we've now got 3 position space and 6 for the shape. So we've got 9 parameters, so gone 4 to 9 for each atom. But again, doesn't look too bad. So we've got the look at things, everything's got better. And at this stage, if we made a mistake, so say we actually want that to be a carbon, we can do the same thing, and hopefully, and something's gone horribly wrong. It's no longer an ellipsoid, it's a tetrahedron. Whenever you see a tetrahedron, it basically means that something's wrong. It doesn't mean that the atom doesn't exist or anything else. It means sort of mathematically you can have a negative ellipsoid, so you can have these shapes sort of with a negative size. Physically that's impossible, but mathematically it's fine. The way the program represents is this tetrahedron. What it basically means is that you're saying there's a sort of, you want to probably have somewhere with much more electron density, sort of a much heavier element there than actually you're stating. So there's much more electron density there on that atom. So it's not completely wrong. It's not as though it's sort of a peak. If it grew to be a huge size, then that probably means it doesn't exist. This just means that you've got probably more electron density, so you want to be looking for a heavier element. So, and you see the R1's got way back up again. So I'll change it back to the oxygen and let it refine again. And go through, yeah. You'll also note there was a Q peak right next door to it, because it knows there should be actually more electron density. Okay, that's good. So we have our skeleton, our heavy elements, and at this stage we're probably sort of not doing too badly. As I say, maximum peak, we're down to a stage where the only peaks left are sort of around 1, which is, if you think about it, is you're looking for hydrogens, each which have 1 electron. Okay, they're involved in bonding and everything else. And actually, on this structure, probably you've got Q1 to Q5, and they all look pretty much sort of. I put the bonding in and get some. There's some extra things, but actually, you've got some bonds here, and they look like it could be 3 around the nitrogen, 2 to the carbon, which is what we expect for glycine. I'll put it back in. So probably I could actually just label them up as hydrogen and see what happens. However, for most structures, so because the hydrogen is involved in the bonding, so if you've got it, so you're only looking for the electron, it's involved in the bonding, the accuracy of where the hydrogen atom is a little poor. So what most people do, and as the first approximation, is you can sort of do a riding model where the hydrogens are placed in sort of fixed positions. So in this case, this is a sp3 carbon. It's going to have 2 hydrogens on it. You can basically do the angles. You've got the nitrogen carbon angle, and you can say exactly where these 2 will be to equally distancing. And the same with the nitrogen here. You've got 3 around it. You can put an angle and so on. Now, what we can do for that is this very simple add H atom. So something, if you're particularly involved in hydrogen bonding and you've got very good data, or you've got other things, then you might want to actually sort of put the hydrogens in by hand, and sometimes you might want to. But generally, for most people, the first thing they'll do is say, why do you put them in by hand? They can be done like this all the time. Their riding model, it's fine. So if it's say the accuracy with X-ray data is still not great. So we'll click add hydrogen, and it will throw in a whole load of hydrogens. And initially, we have sort of slightly lowering the R factor. So these 2 things have got. It looks as though we probably haven't quite got these hydrogens in the right place yet. So I can almost see a triangle of where they should be, but I don't have to do too much. I just have to hit refine again. And it's still rotating, possibly a little bit more, so it's all a shift. But now, if you think my R factor is 4.2, so I'm getting lower and lower R factor, and if I refine again, I might just refine a little bit further around. And okay, I'm now at 4%. So I have my hydrogens on, and I've got some QP. So my shift is still not 0, so I've still got more refinement. So goodness of fit is now green. My max peak, minimum peak are now dark green as well. Ratio is still a little bit lower, but not too bad. So what are my next steps? So again, on the refine thing, there's a thing called a weighting scheme, and this is in red. So I will actually want to do a weighting. Basically, it's something to do, so there's an extra, in effect, fudge factor, so of your data, so just make sure that everything is as good as it can be. So I click on that, and at this stage, things going down, the shift is dropping a little bit. Hopefully this shift at some stage should get to 0, and it's 0.6, but as I say, probably realistically you want it to be 0.000. Depending on some things, you can get away with 0.001 or 0.002, but hopefully we'll get to 0. Often what you actually have to do is increase the number of cycles of refining. As you see, it's been running quickly, but we'll up it to 15. Refine again. Keep going. So we're getting close, 0.02. So you see it's now light green. This weighting scheme is still amber, so we know we want to do another refinement. 3.87, so it's hardly changed. Okay. And now, so we've got a shift to 0, so we're pretty much probably got a completed structure. We've got the Q peaks and everything else. So there are some issues. So one of the things that we want to know is, in theory, there is a circle up here, sort of 2 things to say this formula is not correct. Yet I can see on my screen that I've got 2 carbons, 5 hydrogens, 2 oxygens and a nitrogen. So I've got this formula, so why is it wrong? And actually, so this is something where you have information that you put in at the start that can be wrong, so you need to sort of check two things. So we've got the formula up here, and we've got this thing called the Z prime down here. Now, Z prime is simply the number of molecules in your asymmetric unit. In this structure, and for the majority of structures you have, it will be 1. I think it's about 88% of crystal structures have a Z prime of 1. And then you have all other numbers. So generally it will be a multiple, but you can have halves and quarters as well. But majority will start with 1. And the best thing, if you have any issues, always go with 1 and then see what happens from that. It might be if you've got certain structures, see what happens. But we have to go things. So we now do OK. Now readjust and then adjust the thing. And now this circle thing has got disappeared. So we've got the formula, everything else correct, which is a good sign. However, we've made a change, so what we should always do when we make a change is click refine. So each time you do a change of anything, you should always try and change the crystal structure. Okay. Now, yep, that will be enough. So basically, we're probably at the end of solving and refining the crystal structure. So we just need to do some extra solves. This is almost the dotting the I's, crossing the T's to make sure everything is correct. So the first thing we actually want to do is produce a file we can output. And the absolutely international standard is a CIF file, so crystallographic information format or file. And the way to actually generate that file is this thing here, which initially says no actor. So all we want to do is change it to actor and then run another refinement cycle. Okay. And we can keep that. As I say, at this stage, when we're doing the refinement cycles, you'll notice that actually my R1 is not changing. Everything else up here isn't changing. But sometimes, sort of, as I say, each time you make a change, it is best to run the refinement cycle so that everything is as you expect it to be, the sample, the data, and so on. So we are going to, that CIF file does need to be curated as well. So there's information and so on. But before we get to that, let's do. So yeah, what I'm going to do first. So as I say, we've been in refine the whole time. Check, everything else looks good, and I'm quite happy with things. So we can go through the details. So I'm going to ignore draw for now, and we're going to go on to report and click on the arrow next to report. Now, often when you do these things, it comes up with conflicts, and basically it's if you've got a metadata file and a CIF file, and it will compare them. And if you actually notice, the only difference between the top things is that one's to 3 decimal places, the other one's to 1. Technically, I guess we did actually sort of say the crystal was 0.4 millimeters in size. That's what it actually says. But whether it's 0.400 or 0.40 or 0.4, I don't know. So we can click. Generally, if you've got any conflicts and you're all worried which one to do, the first thing is the one that is the CIF file. So this is the one that's generated from the program, is the primary one. So that's the one you should use. So we can just click and say use all. It doesn't matter. As I say, if you do need a thing, you can adjust them later. Now, realistically, there are in the report, we're actually going to generate a report at the end, but there's three of the tabs are the ones that probably you're going to have to fill in. So first of all, collection. I know the structure is glycine, so generally you want to have an ID that might be different from the name and things. And you can also, if you wanted, there's ways to say who ran the structure and you operated it. So we've got an ID there, that's fine. So what we want instead, probably a thing again is metadata. So we've got the crystal, might have a name for things, but probably vital things are the size and shape of the crystal. So generally, so each time you run a crystal, sort of the diffraction data will be slightly different depending on the size and things. But if someone wants to repeat it, they want to look at things, they'll see what structure you had, and everything else, and go through. If you want, there's other information here, sort of preparation. So if you're actually trying to publish it or something, all this will be filled out. But realistically, the absolute minimum thing is to know the size and shape of the crystal. And finally, the third one is diffraction. And this one, you'll have something about, sort of hopefully we'll have something about diffractometer that you ran on. It's not a Crystal Lab Mini. And then information, and probably the other bit is actually the cell temperature. So this is the data collection temperature, and the temperature is actually vital, depending, especially when you're fixing hydrogens. The temperature does make a difference to the size you have, and a crystal structure will be different at different temperatures. So if there's slight variation, you've got thermal expansion, so the unit cell size will be subtly different, and so on. So you will have things. So if you don't know the temperature, then you can't actually say this is a crystal structure. So you do need to know what the temperature is. And again, if you wanted, you could fill in extra details there. So those three, that information does need to be hand. If you haven't got it, you've got to find out and go back and sort of talk to the person who ran the crystal to find out what was the thing. Generally, sort of temperatures is either room temperature, so that'd be something like 293 Kelvin, 298 Kelvin, depending where you are in the world. And cold often is 100, 120 or 150 Kelvin. These are a little warmer, so the setup we're looking for. And those three things, again, we've got a whole load of things, and you've got more information you can get, but I've got those three bits of information. I've put some tiny bit in, so I will click refine again, just run a refinement cycle. It's added that information into the SIF things. We're up to. So, final thing. Got a nice sort of structure here. Most people, sort of the one thing you actually want when you have the report is to have a picture. So the third tab here is the draw tab. Now, again, everyone has their own opinion of what they actually want. Now, the one thing is, what you will have, you'll see that while I've been processing, there's been some information behind the structure, continuously scrolling up the screen. It's got a few lines. When you do the draw, actually the values will sort of, that will be disappear and we'll have a blank screen. Now, the other thing is my screen is white. If you have sort of the function key, so there's function F2 and function F4. So F2 gives, goes two colors, and F4 gives you the graded color and so on. Generally, when I want diagrams, I always have it white. So all my Olex is always in white anyway. But if you need to change the color, that's it. So the F2 and F4, and cycle through those, and you will end up with a white tab, sort of a white background. What I'm actually going to do initially is remove the labels so I can't see them. Everyone has ideas of how they want labels, or whether you want everything labeled, whether you want sort of thing. So there's a whole things here. You can have selected. So if I just click on this oxygen, click selected, I now have a labeled atom. I can have heteroatoms labeled. I can have non-hydrogens atoms. I can have everything labeled. If you select sort of the hydrogens as well. Generally, most people, unless it's involved in hydrogen bond and is very specific, most people probably ignore sort of labeling up the hydrogens. It starts to get cluttered. And in fact, a lot of the time, you'll also won't label the carbons. And again, because there's so many of them, if you don't like them, you can always delete the labels if you only want some of them. So now I've gone to hetero, let's do non-hydrogen, and then decide I don't want the carbon. Again, select an atom. Left click, once it's highlighted, I can do what I like, I can delete it. Same with that carbon, I don't want it. If you don't like its position, if you hold the shift key down while it's highlighted, we can move it around. If you don't hold the shift key down, you'll move the whole structure. And then once you're happy with its position, click it again. Thanks. If you notice, when I'm moving the structure, the labels move with the structure, but sometimes they end up. So if I move it to there, it's now not a good position. So I'd want to move that label again. But hopefully, at some stage, there will be a position where you have some nice labels. Position. Just something else. If we've got, at the moment, they're in black. If you don't like the color, if you wanted something else, choose label color. And it's the ambient font, so I can pick and I could have it as, I don't know, that orangey red. Okay, there it is. Actually, I don't like that. I'll go back to black. Okay, but you can do what you like. And again, preferences, so people have their own preference of how they like to have a structure. But at the moment, I'm quite happy with that. So once I've decided that everything is labeled as I like, you've got a whole series of options, but generally the simplest one to do is bitmap. So there's a PNG, transparent background. Again, you can do resolution. So some journals or things will say they want a 600 dpi resolution. If you only need 150 or 300, you can change it. And again, size, put some more things in. You can have it as different sort of types, but the whole thing with the PNG is you can have transparent background, so you can put things and you can overlay it onto a structure, onto other pictures and other things. So the white becomes transparent, which can be useful. So that oxygen, I think, needs to be moved a little, but otherwise, I don't know how to go. And the first time it does it, it will produce a structure, a label, a sort of, as I say, the name is sample data 1.png. So if I wanted a different name, I'd change it up here, and it won't automatically overwrite. So if I've made one image, if I do a go again, it will say it exists, and then I would have to change the name. So don't worry, that's the thing. So we now have a nice diagram. As I say, anything in the background won't be seen. So now we go back to report, and we have sort of data. We've got the report, so I want to have that image put in. And what we're going to do is generate a report, create a report. So this is very simple HTML, which I will now have to just change. Use that. So here is the data. Hopefully you can see now an HTML file with sample data. Okay, I can change the name to something more appropriate later, but you've got the diagram I put on with the labels, and you see that I now don't have the information down the back, and it has the information. So collection, formula, unit cell, and basic information. And you can then edit this to what you want. You can copy the information, decide what you want. So that's the sample data, and that's the CIF. Okay. And that is most of the thing. I will go back to the Olex2. And that predominantly is the end of the presentation. I will just check things. So we have what you'll have created is a CIF file, we created a report, and we can go through.